All right. Good afternoon, everybody, and welcome to the 6th plenary session of the 70th International Astronautical Congress. We're here to talk about the Europa Clipper mission, and you probably all knew that already. So, my name is Deepak Srinivasan. My role on this mission is the telecommunications system engineer. So it's my team's and my job to make sure we can both talk to the spacecraft, as well as make sure that all of the data that's just waiting to be uncovered on Europa makes it down here for all of us to learn. Now, Europa has consistently ranked as a top priority in NASA's decadal missions. The thing is, to actually execute a mission to make it happen is really, really hard. So that's why NASA has asked not one, but two organizations, the NASA Jet Propulsion Laboratory, as well as the Johns Hopkins University Applied Physics Laboratory, to execute this mission. The theme of this Congress has been the power of the past and the promise of the future. So between our two organizations, we have a combined 159 years of spaceflight heritage. So we're going to leverage all of that to promise that we're going to get data back from Europa that's going to literally change our understanding of life itself. To set the stage, I want to bring it back to Earth, our own home planet, the most precious piece of real estate in the solar system. I kind of like it. Now, Earth, as nice of a day as it is outside, is a planet of extremes. We have tundra that's been frozen for millennium. We have searing hot deserts with only trace amounts of water. And we have places like this, the depths of our oceans, beneath miles and miles of water, denied sunlight, hydrothermal vents heating up the water to more than 400 degrees Celsius. But the pressure of those same miles of water doesn't allow the water to boil. So this is extreme areas. Yet, wherever there's water, no matter how extreme an environment, we find things like this, life. Life not only exists, but you see it just flourish. Wherever you find water, you're going to find the most incredible things. Now, Earth is not the only ocean world that we have in our solar system. There's several ocean worlds out there, many of them orbiting our icy moons. Now, this is a really exciting time for all of us. We're on the cusp of exploring many of these moons. We have the Dragonfly mission that's going to be exploring Titan soon. We have ESA's JUICE mission that's also going to be exploring these moons. And we have the Europa Clipper. So to talk more about Clipper, we have this exemplary panel of people where we're going to discuss all different aspects of the mission. We're going to start off with Bob Pappalardo from JPL. He is the project scientist for Clipper, so it's his job to make sure that we're deploying the right instruments and using them in the right way to answer all the questions that we want to have answers to. Sorry. After him is Karen Kirby from APL. She's the deputy project system engineer, and for the last several years, she has been instrumental in designing the spacecraft that's going to be able to withstand the harsh environments. After Karen is Jennifer Dooley of JPL. She is the project system engineer of this mission. So she has overall technical authority across all aspects of our mission. Tom Magner from APL is the assistant project manager, and he's going to talk about how we brought together this fantastic team of people to pull this off, and how we collaborate. Lastly, we have Bill Nye, the CEO of the Planetary Society, and he's going to talk about how Europa has just captured our imaginations and how we can advocate for these missions to continue to happen. So with that, I would say we're going to dive into the science, but that's just too bad of a pun, so I'm not going to say that, but here's Bob.
Clicker. Oh, this is it.
Oh, you can go there.
Good afternoon. Let's see. There we go. In 1610, Galileo Galilei turned his rudimentary telescope to Jupiter. And what he found, he sketched there, that there were 4 large moons that night to night he could observe orbiting around Jupiter. He found that Jupiter was a center of motion and that Copernicus, 50 years earlier, was right. Galileo had changed our world forever. The 4 Galilean moons, as they're now known, are named for him, have been revealed by spacecraft, the Galileo spacecraft, in fact, which orbited Jupiter from 95 to 2003, gathering data about these 4 moons and the giant planet itself. Well, one of these moons, Europa, has the potential to change our world again. Europa has a bizarre surface, much different from what we see on our Earth or on our moon. Most of what we see here is ice. That bright stuff is ice. There are not many craters, so the surface has been repaved in the last 65 million years, since the time dinosaurs roamed our Earth. There are ridges and chaotic terrain and these freckles that are known as, by their Latin name, lenticulae, that pepper the surface. And this geology in ice hints of an ocean deep below the surface. The interior of Europa, here's what we think we know about it. We think there's an ice shell about 20 kilometers thick, 13 miles, above an ocean about 80 kilometers thick, in turn above a rocky mantle and an iron core. So what allows Europa out there in the frigid outer solar system to have an ocean beneath its surface? Well, Europa orbits Jupiter in a somewhat eccentric orbit, slightly non-round orbit, and as it does, it goes around every 85 hours, every 3.5 Earth days. It flexes. When it gets a little closer to Jupiter, it stretches out. A little farther from Jupiter, it contracts. And this flexing back and forth every 85 hours generates heat from friction. So this tidal heating is what maintains an ocean at Europa. If we were to gather all of Earth's water, ocean water, into a ball, we'd see that Europa's suspected ocean water is about twice that volume. So Europa is the size of Earth's moon, yet contains more water than all of Earth's oceans combined. The best evidence that we have for an ocean today at Europa, while some evidence comes from the geology and some comes from the math of calculating how much tidal heating there should be, the best evidence comes from the magnetic measurements at Europa that were made with the Galileo spacecraft's magnetometer. Europa is moving through Jupiter's magnetic field as it orbits around Jupiter, immense magnetic field. Well, if you carry your keys or your cell phone through a metal detector at the airport, the metal detector beeps because the metal in your pocket conducts electricity and sets up a secondary magnetic field. It makes the metal detector go off. Europa is moving through Jupiter's magnetic field, and it essentially set off the Galileo spacecraft's magnetometer because Europa's interior is able to conduct electricity because of a saltwater ocean beneath Europa's surface. On Earth, just about everywhere there is liquid water, there's evidence for life, including on the ocean floors, as Deepak showed, where water seeps into cracks in the rock, and where that rock is hot at the mid-ocean ridges, that water becomes charged in nutrients that then come back out into the water and condense in these clouds of black smoke, as it's known. And on the ocean floors, the chemical energy from that material powers bizarre life, giant tube worms and crabs. In a place that's completely devoid of sunlight, life flourishes on the Earth. The same could be true of Europa's ocean, which seems to have the so-called ingredients for life. Liquid water, much more than all the Earth's oceans. The elements from which organic molecules can be built, things like CHONPS. And chemical energy, that is the energy that could potentially power metabolism. The surface of Europa is very oxidizing, we think, very oxygen-rich, and the ocean floor is probably reducing, hydrogen-rich. So if we can get those, if Europa can get those oxidants from the surface into the ocean, then there could be the chemical energy that could power life. And then finally, we suspect that Europa's ocean is ancient, that it's been simmering for 4 billion years, and the level of current activity and past activity is something that's relevant to habitability through time. So these are the big picture issues that we have an idea of, but we need to test with the Europa Clipper mission. So the mission has several objectives. We want to understand the ice shell and the ocean of the moon. How thick is the ice? How saline is the ocean? What are the mechanisms that can get stuff from the surface, including oxidants, down into the ocean, and vice versa? So when we look at the surface, are we able to decipher the ocean properties? We want to understand the composition of Europa. What is that dark reddish stuff that's all over the surface? What is it telling us about the nature of the ocean and about how materials are processed on the surface? The bizarre geology, these double ridges, the chaotic regions, what forms the geology and how is liquid water involved in that? How active is Europa today? From the Hubble Space Telescope, we have an idea that there are glows on the limb of Europa of hydrogen and oxygen. Is that indicating that there is active venting at Europa today of liquid water from the subsurface into space? And like Enceladus at Saturn has plumes, and Cassini was able to fly through them, can we do the same with the Europa Clipper mission to sample Europa's interior material directly? And as we gather all this data, we learn about areas that might be especially interesting to explore in more detail in the future if we were to send a landed mission to Europa sometime. So that's the big picture science for Europa, a fascinating place that can tell us about how common life might be in our solar system and therefore throughout the universe. So next, Karen Kirby is going to tell us a bit about the Europa Clipper spacecraft.
Okay, NASA has selected the science investigations for the Europa Clipper mission to address the decadal priorities for exploration of Europa. We have 10 science instruments that are currently accommodated on our spacecraft, and I'll introduce these instruments briefly and tell you what we're going to learn from each of them about Europa. Okay. So I'm going to start with our in situ instruments. MassSpex is a mass spectrometer that will sniff the atmosphere, and SUDA is a dust analyzer that will collect particles that are ejected from the surface of Europa. These will both provide composition information about the atmosphere as the spacecraft flies through it. Next, we have magnetometers that are going to be measuring the magnetic field around Europa, and PIMS, which is a Faraday cup instrument that will collect particles from the plasma environment as we fly through. These two together will provide ocean property information such as thickness and salinity. Our remote sensing instruments, I'm going to start with a couple of spectrograph sensors. We have both an UV and an IR spectrograph sensor, and these are going to provide composition and activity information about the surface of Europa. UVS is also our plume search instrument that will be monitoring for plumes so that we could further investigate plumes on future flybys. And MISE will provide a map of organic compounds on the surface of Europa. Our imaging instruments are next. We have the ice investigation includes both a narrow angle camera and a wide angle camera. These cameras will provide almost global imaging. They'll be imaging over 90% of the surface of Europa, and some of this at very high resolution. eThemis is our thermal imager, which will be looking for hot spots on the surface. They'll be measuring surface temperatures on the order of 100 Kelvin to 2 Kelvin precision and accuracy. So with both of these instruments together, we'll be going after geology of Europa, and we'll be obtaining global maps of the surface of Europa. And these also will be used to support our final instrument, which is our ice-penetrating radar, REASON. It's a dual-frequency band sounding radar that will be penetrating the ice on Europa and will be providing information about the ice properties and also targeting the understanding the subsurface ice-ocean interface on Europa. So we have a very rich suite of instruments on this mission. And I'm going to switch gears now and talk a little bit about the spacecraft design. So just for kicks, this is a standard US-sized basketball court. Since we're in the US, it's appropriate to have the US-sized court. And here's our spacecraft. So you can see it's huge. These, with our solar panels fully extended, it's on the order of 30 meters in length. We expect this to be the largest spacecraft in deep space when we launch. It's a challenge to build something this big, as many of you know. But really, our biggest challenge is surviving the radiation environment. Because Europa is in Jupiter's magnetosphere, and the magnetosphere accelerates and traps high-energy particles, it provides a very intense radiation environment. And this has been an issue for close-up exploration of Europa for a long time. So I'll talk more about how we're going to survive in this radiation environment, how our spacecraft will survive, and our instruments. But first, I'll also talk about another challenge we have, which is the thermal extremes that we'll see during this mission. We're designed to survive hot temperatures up to 100 degrees C on our solar panels, down to minus 230 degrees C range, which is what we'll be seeing when the spacecraft is at Europa at 5.5 AU in the Jupiter environment and during our longer eclipse periods. So we have radiation and cold temperatures combined. This provides a very challenging environment to operate and survive through. One of the things that we're doing on this mission to help with that is we're using a radiation vault design. If you look on top of the spacecraft, you see sort of a rectangular shape. This is our radiation vault. It has most of the spacecraft electronics are housed in this vault. Roughly half-inch thick aluminum and tantalum layers provide that shielding for us and really knock down the radiation environment for the sensitive electronics. What really, though, makes this mission possible, I'm going to say, is this flyby mission concept. So there have been studies for missions to Europa for many years that have been going into orbit around Europa. And this really provides a very short mission because of that intensive radiation environment. So what we're doing with this mission that's really a game changer is we are staying in Jupiter orbit and then targeting a very close approach flyby of Europa on every orbit. So we dip into that high intense radiation environment, we turn on all of our science instruments, collect a lot of data, and then move away from that environment where we then send the data down to Earth, recharge our batteries, and get ready for the next flyby. And you can see the Geiger counter is attempting to show that we really get that radiation dose in spurts as we do those flybys. And then there's a dosimeter showing the total radiation dose. We're building that radiation dose up gradually over the course of the mission. And this way we can spend years exploring, many years in this environment, exploring Europa, rather than days or months. So Jennifer's going to tell us more about how we're going to fly this mission.
All right. So first, I'll give you a little bit more context and kind of a frame of reference for the spacecraft. So we talked about the size of it a little bit, let me give you some scale for the mass of it. Everything we build, the structure, the propulsion system, all the electronics, the instruments, together that weighs about 3 tons, 3,000 kilograms. And we add about as much fuel to that. So all total, it's about 6,000 kilograms. And for reference, that's about the size of an African elephant. The other thing, we already looked at how large the solar arrays are. We're so much further away from the sun at Jupiter, and over the course of the lifetime, the radiation environment takes such a toll on the efficiency of the solar cells that by the end of the mission, that solar array produces about 700 watts. And for reference, the hairdryer in my hotel room this morning operates on about 1,900 watts. So this is less than half of the energy we use there. Let's see, so we have a suite of instruments that Karen talked about. There's a set of remote sensing instruments, and those are largely mounted on a single deck that we, when we fly by Europa, point directly at the surface. And we also have a suite of the in situ, or the sort of direct sampling instruments that we point in the direction that we're traveling at that point of closest approach. We have large deployable boom antennas for the radar, and we also have a 5-meter boom for the magnetometer, which, as we talked about earlier, was one of the key measurements that pointed to this ocean on Europa. On the right, you can see an inset from the video Karen just showed. Each one of those orbits is a petal. Together, they look kind of like a flower, and that set of petals is a tour. The team has done a variety of tours, but they share some characteristics, and we're always working on those and getting those evaluated by the science team. Each one of those petals is about 14 days. As Karen said, we come in, we dip a toe into the radiation environment, we collect a lot of data quickly, we come back out and collect on the solar array to build up on our batteries. We return data back to Earth. That takes a long time. And we're also dissipating some charge that's built up over the course of that exposure, and that helps us avoid damage to some of the components. What I'm going to do next is show you, for all of those pieces of the petal, we call it the encounter, that are very close to Europa, I'm going to switch now and show you just those segments of the petals on a Europa-centric frame, so you can see how over time, over about 3 years, we build up this global coverage. So what you're looking at here, right, we were looking at a projection before. What you can see is that for each one of those petals, the mission design team is varying the latitude, they're varying the cant angle. You can also see that there's much fuller coverage on one side and its opposite side. Europa is tidally locked, like our Earth's moon, and that means that the same side is always facing Jupiter. And it's just a feature of the way the mission design works, the way the tour works, that you get most of it on the side that is facing Jupiter and the side that's opposite it. And what this gives us, at the closest approach in these little segments of the petals, the warmer colors, so the red, is about 25 kilometers from the surface. And it goes out in the white to about 4,000 kilometers. And so when we're very close, we can get high resolution images. And when we're further away, they're a little bit lower resolution, but we have very good coverage. We get larger areas. And what you're seeing on the right, those are projected classes of measurement on a Europa map that give us a sense for how that coverage builds up over the course of the tour. And you can kind of see some, line features that sort of match up with these segments of tours. All right, so now what I'm going to go to next is I'm going to take you on sort of a day in the life of one of these segments on the tour. Basically, there's a lot of activity that happens quickly. Let's see. Okay, so what I'm going to show you here we're going to start with this video. We'll flip to a little bit different point in the video when I hit the next button. And we're going to start having just completed our last downlink to Earth. On the lower right, you'll see a little map that shows the relative position of the spacecraft with Europa and Jupiter. In the top left, there's a little ticker for the altitude and the relative velocity with Europa. And on the lower left, there's kind of a key for color. It's hard to keep up a little bit. I know I watched this video many times trying to pick out all the pieces. So I'm going to talk sort of in a little bit more generalities as we go through this. But you can just see for the different colors, those are different instrument measurements. All right, so this video starts about 13 hours out from closest approach. We've just turned away from our Earth point, and we have oriented so that the remote sensing instruments, all those cameras and other imagers and spectrometers, are pointing at Europa. We have our magnetometer is on, and our plasma instrument is collecting data. We're taking UV scans and images, and we off-point sometimes for calibrations. Now we've reoriented the solar rays so that when we flip, we'll have the radar antennas pointed towards Europa when we get there. Let's see. And so we start to take more images. It started off with more of ultraviolet and imagers, and now we're adding some of the thermal imaging, spectroscopy with MISE. And as we're getting close, you can see that the pace starts to pick up. There are some coordinated measurements. We're doing some wide angle measurements and finer cut. We're starting to come in close, and pretty soon we're going to see the radar come on. And now we're at closest approach. And what happens on the outgoing leg is very analogous. So we use both of those to collect all of the images that we're trying to get. You can see we're producing most of our data very quickly around this point. This whole video represents about 20 hours, when that whole orbit, that whole petal is about 14 days. On the outbound, there are also some differences having to do with setting up for trajectory cleanup maneuver, and also starting to prioritize the data and sort it for eventual downlink on the 3-meter antenna. So there we go. And essentially what we're doing then is we're catching our breath, starting to send that data down, and planning for the next, for 14 days from now when we do our next encounter, and the 14 days after that, and after that. So with that, I will turn it over to Tom.
Hello. So I'm going to talk a little bit about the teamwork and partnerships that we formed to execute this mission. As complicated and as large as it is, we felt teamwork and partnerships were going to be very important. So one of the things we did is partnered on the development of the spacecraft testing and integration with the instruments. And that partnership was between JPL and APL. And so what JPL does is builds the avionics module that Karen talked about that sits on top of the spacecraft. There's a boom that gets that magnetometer away from the spacecraft, a launch vehicle separation system, an adapter, all of the flight software. And then the way we do thermal on the spacecraft is a heat redistribution system, or HRS. So rather than heaters and radiators, we use heat that is generated in the avionics vault and spread that to the rest of the spacecraft to keep them all within flight allowable temperatures. At APL, Deepak is building the RF module. In that, we've also partnered with Langley to test the high gain antenna. That's a 3-meter Ka X-band antenna. We're building a propulsion module which sits in the middle of the spacecraft there, that basically holds almost all of the components of the spacecraft together. Embedded in there is the propulsion subsystem, and we partnered with Goddard and Marshall to do that. Goddard to build it, Marshall to do component testing. The solar array we're procuring from the Dutch Airbus. We're building a radiation environmental monitor that'll allow us to keep track of how much radiation the spacecraft has accumulated through the various orbits of Europa. And we're going to build the electronics that drive that HRS heat redistribution system. Jointly with JPL leading, we're going to integrate and test the spacecraft. Then for instruments, we have 8 instruments that are PI instruments that were selected by NASA headquarters, and 1 instrument that is a project-provided instrument. So starting on the left, we have the REASON, which is the ice-penetrating radar provided through Don Blankenship at University of Texas. There's 2 instruments that are coming from Johns Hopkins Applied Physics Lab, the Imager and the PIMS instrument. Southwest Research Institute is providing the mass spec and the UV instrument. JPL is providing the shortwave infrared spectrometer. University of Colorado is providing the dust analyzer. Arizona State University is providing the thermal imager. Then the one instrument that is a project-provided one is the magnetometer. Margaret Kilvison is the science lead for that team that's helping the project determine how to build that instrument. Then we formed also, I'll say, mission partnerships. So again, JPL and APL collaborated and are partnering under JPL's lead center to do all of the project management for the mission, drive the science, do all the system engineering, come up with how we're going to navigate the spacecraft, how we're going to operate the spacecraft, oversee the payload management, and eventually operate the spacecraft in orbit. And then you can see here, so we're a very diverse, or let's say spread throughout the country between Goddard, the field centers, JPL, APL, and all the instrument providers. So one of the things this is becomes a challenge for all of us is how we communicate, how we collaborate. So we use obviously all of the usual techniques of WebEx and other methods, face-to-face meetings, but we've also come up with some unique things we do. So what you see here, I'm going to start the movie in a second. This is a VR version of our spacecraft as we're designing it. So you can see kind of in a lighter color the spacecraft. The people you see are APL people, because this is actually done at APL, but also done at JPL. And you will start seeing, and I'll point out, JPL people who are participating from JPL in this session where they're talking through some engineering problems and are participating through VR. So here I started. So everywhere you see a name and you eventually see like a little headset is a JPL person looking at that model. They're talking to each other. They're pointing out maybe a problem with running a harness and whatever. So we can get a lot of work done in an environment like this. To try to do this over a phone where both of you are looking at 2D PowerPoint just wouldn't cut it. So this is one of many ways that we've come up with doing these things. This has been very effective for us, so we're very happy with it. So with that, I will turn it over to Bill.
Thank you. Greetings. You're welcome. No, really, seriously, no. Hi, I'm Bill Nye from the Planetary Society. The Planetary Society, if you're not familiar with us, is the world's largest independent space organization, and we advocate for space missions, and we are honored to be part of the Europa Clipper because there's reasons to do these missions that are just deep within us. And you can talk about budgets, you can talk about hardware, and that is, of course, fascinating to me, but in the bigger picture, there are 2 questions that everybody asks. And if you meet somebody who says that he or she has never asked these questions, they're lying to you. And if you're in middle school, they're lying to your face, that's way more serious. And the first question is, where did we all come from? Where do we all come? What are humans doing here? What are shrimp doing on the ocean floor? How did we all get here? And then the second question is, are we the only ones? Are we alone in the cosmos? And these questions are fundamental. And this mission like Europa Clipper is how we work toward answering them. My friends, if we were to find evidence of life, let alone something alive, on another world, it would change this one. Everybody on Earth would feel differently about being a living thing in the universe. It would change the course of human history. We mentioned earlier about Copernicus or Galileo. These investigators changed the way everybody thinks about our place in space. And what is wonderful and charming and compelling about missions like Europa Clipper is not an individual that did it, not an individual person who made these discoveries, although Marky Kivelson, using magnetometers, discovered the ocean on Europa, the sub-ice salt water on Europa. This mission is done by a team of people, an international team of people. That's because space exploration brings out the best in us. So if you are interested in birds, you join the Audubon Society. If you're interested in certain environmental issues, you join the Sierra Club. If you're interested in space, we recommend you join the Planetary Society. And what we do is we innovate. Tomorrow we'll have a brief thing about our spacecraft. We educate. We have, I believe, first-class journalists who will talk about this mission from now until when it flies and all the discoveries it made, and we will put images from this mission on our website and so on in the coming decade. And then we advocate. We spend time in various government organizations advocating for the importance of these missions, because what we spend on space is so small compared to what we get out of it when it comes to any mission to any planetary body. So as I say, I'm honored to be here. Thank you all very much for including us, because when we explore space, we solve problems that have never been solved before. And I have been asked many, many times over the years, why do you build a mission like Europa Clipper? What are you going to find out there? And the answer is, we don't know what we're going to find. That's why we're going. And as one of the founders of the Planetary Society, Bruce Murray was head of the Jet Propulsion Lab during those extraordinary missions, Viking landing on the Martian surface, and Voyager missions, which are still flying on the outermost reaches of the solar system. He apparently was in meetings in the 1960s when one of the Ranger spacecraft, this was a spacecraft, I was a little kid, I was literally on my knees watching on all three networks, which is all we had, the lunar surface coming up on live television. They would smash into the lunar surface. One of these spacecraft was sent to Mars. And in the early days, apparently people suggested that you don't really need a camera. You don't need cameras. Pictures would be a publicity stunt, be for the public. You imagine a space program without pictures? I mean, who would care? And so we will send back, Europa Clipper will send back images and data that will just change the way everybody feels about us and our place in the solar system. So I'm very excited to be here, and I'm very excited to hear what questions come from the audience. Deepak, lead on.
All right. So thank you very much, Bill.
Oh, no, it is we who thank you. Oh, no.
All right, and again, if you check out either the IAC 2019 app or slido.com, you guys can start submitting some questions or voting up various questions that have already been submitted. So here's one that actually we hear about a lot. So how does Clipper produce knowledge and resources for a future Europa sample return mission? But I'll expand that to just a lander mission as well. And are we planting any seeds to push for that? So I'm going to hand that one over to Jennifer to respond.
So primarily, the purpose for Clipper is to explore habitability. As part of that, we acquire a lot of local scale data. So that's some of the imagery that we take at the, around the closest approach. For example, we will get down to images that have a pixel scale of, at the best about a half a meter. We also take stereo images that can be used to reconstruct topography, and that's together with other information about, what thermal variations, composition variations, local geology, and all of that information together really is supporting the primary goals for Clipper. But just like happened with the Moon and Mars, those are the kinds of data sets that then produce the context and the understanding that allows the next step of landed missions.
So at a half meter scale, right? So when I was in Carl Sagan's class, I really was, back in the disco era, he put up a slide and said, what do you make of this? It was an image from space in the early days, and he was trying to get us to determine whether this sequence of images we were seeing was alive. And it was a picture from space of a swimming pool full of people. And the people were just dots, just pinpricks on this image. But if you're at a half meter, you're going to see Europanians if they're out there doing their Europanian thing. I mean, it's really extraordinary when it gets that accurate or that high resolution.
All right, thank you very much. That's a lander mission or anything like that. It totally evokes the imagination, and we hope that as time goes on, we will be able to do such things.
And I hope you guys can do this in my lifetime.
Me
But
too.
I'm not joking you. It takes a long time to get to these distant worlds and to get data back, and then it takes a long time to evaluate those data and decide what to do next. But I'm hoping to be alive when we find evidence of life out there.
As Bill always says, that will certainly change the world. So the next question I'm going to ask is, this is going to go to Karen. So can you explain how radiation from Jupiter affects Clipper's electronics?
Yes. Can you hear me? Yeah. Okay. Yeah, there are a number of effects that we get from the radiation environment. As I mentioned, there's just the total dose that we have to survive and that we shield for that. There are other effects from the radiation that can cause things to upset, can cause also charging on the surface of the external surfaces of the spacecraft. And so we do a number of different things to try to mitigate that. We have conductive surfaces on the external surfaces of our spacecraft because charging could interfere with some of our science measurements. We have circuitry that we use to protect from faults propagating to other circuits. We also have redundancy on board. So we use a number of different techniques to protect from that environment. We also do some testing. Before we launch, we need to make sure that all of the components, all the parts, all the materials at the part level and then at the box level can survive the radiation environment. So we do radiation testing at different exposure levels that's well beyond what we're expecting to see in our mission.
All right. Yeah, so that, as Karen was saying, that it's a super difficult challenge to make a spacecraft work in that environment, but that's what the team's up to do. So the next question I'm going to pose is going to Bob. With ESA's JUICE mission, which has a similar profile, how are we, and if so, how are we collaborating with them to make sure our measurements are collaborative and working together and not stepping on each other's toes?
Yeah, we have an informal partnership with the ESA folks where we've had so far a couple of scientific meetings where we get together and talk about the potential synergies and complementarities between the two missions. The JUICE mission will explore Ganymede in detail, while the Clipper mission will explore Europa in detail. The JUICE mission makes a couple of Europa flybys, the Europa Clipper mission makes several flybys of each of Ganymede and Callisto, and JUICE flies by Callisto as well. So, so we've talked about the potential complementarity if we're in the system at the same time, especially for the magnetospheric science. To understand 2 points in the magnetosphere at the same time would be fantastic, and we'd learn a lot about the magnetic environment. And whether or not we're in the system at the same time, we'll be able to compare the results between the two. What did the JUICE radar determine at Europa compared to what the Europa Clipper radar was able to sense at Europa? So we're definitely talking about the potential for the science benefit of having two missions.
And Bob, the magnetosphere is really what causes the radiation environment to be so severe, right? It's holding these charged particles that you're flying through.
Exactly. The charged particles are both trapped from the solar wind, these charged particles, and many particles escape from Io and become charged and then get accelerated by Jupiter. Jupiter acts like a giant particle accelerator, and then they slam into Europa and the other satellites and slam into our spacecraft.
All right, so the next question I'm going to pose over to Bill. Do you think that Europa will be the next colonized destination in our solar system?
Okay.
How long until that'll happen, Bill? Tell us.
Okay, everybody. First of all, in the planetary community, we discourage the use of the verb colonize. We prefer settle. Colonizing has gotten a bad rap, understandably. And just to put it simply, no! It's fantastically far away and cold. There is no air, there's nothing to breathe, there is nothing to eat. Now, people do go to Antarctica and do their thing, but nobody goes, really everybody, nobody goes to Antarctica to build a school and swing sets and live there indefinitely. So just as far as this romantic notion of just going out and setting up shop in different planetary bodies, I really encourage us all to think it through. And if we were to just do it, just go nuts in science fiction fashion, what if we were to discover Europanians of some sort? These could be microbes or the deep ocean vents with its ecosystem. What would we be doing there except messing it up? So I would say no, we probably will not settle Europa. However, if I had a chance to go there and walk around, or go there and go down through the ice tunnel of the future that we build with that lander and its ice melting system, that we have. That would be cool as long as I can come back. If we ever, organize the Solar System Cup with some Quidditch game between planetary bodies, I'm always going to be for Earth, you guys. People say, what's your favorite planet? And they, the young people for a long time wanted me to say Pluto. No, Earth is my favorite planet. This is it. This is where I'm from. All my friends are here. The food's great. And so just when you pose those questions, they are cool questions, to be sure. Are we going to settle another world? But practically, it is some kind of difficult. I mean, we are having some difficulty taking care of this one. And so to try to take care of a place that's so hostile, really difficult. But as I say, to explore it is it's just so compelling. Let's go. Let's go.
We are going. Let's do it.
2023. Let's go.
That's right. So the next question, there's a few questions on this topic I'm going to pose over to Karen. I'm going to kind of combine these questions into one. So when you're out of Jupiter, that's roughly 5 AU from the sun. So the sun is kind of small, and that's kind of what motivates us to have such large solar panels. And even with solar panels the size of a basketball court, as Jennifer said, we get less power than that of a hairdryer, which is kind of really cool when you think about it. But given all those challenges of having to fly such a large spacecraft, did we consider any other possible power sources other than solar panels?
We did. We started out life as a nuclear-powered spacecraft. It turns out it was a good thing we made the switch to solar because we would have needed way more nuclear power sources than were available for us to use. They put out a limited supply, and then they degrade over time as well. So our solar panels are giving us more power than we would have had available. But we did do a trade study on that. And Jupiter is in a place where it's sort of borderline, you know, as you get into the outer planets further out than Jupiter, yeah, you need those nuclear power sources. But at Jupiter, we can still get enough energy and power from the sun, and we supplement with our very large batteries that we could actually make this mission work solar.
All right. Thanks, Karen.
When you start using plutonium, it gets expensive.
It gets expensive. There's a lot of other things that gets involved.
Just more about me, finally. No, when I first took over at the Planetary Society, one of the things that we advocated for very strongly was the production of plutonium-238, which is this unique isotope that is well suited to these missions. But it's made in very small quantities. I mean, you just can't just go online or go on the web and buy plutonium-238. It's if you can do it with solar, it's just so much less trouble. It's just so much less trouble.
Absolutely. So the next question I'm going to pose over to Jennifer, and Bob might chime in as well. So we saw that there was, you know, many flybys of Europa, and we're going to see different portions of the moon with each flyby. So how do we select what specific areas we want to fly by? And do we have an agile mission such that we can change things on the fly, literally?
Sure. Why don't I start? This is specifically not a targeted mission. That is, we're looking at the trajectories available because Europa is fascinating essentially everywhere. So wherever we go, we'll sample ridged plains and we'll sample chaotic material. Now, I'm a scientist, and the science team is made up of scientists. So when we see that, oh, look, if we just moved one of those trajectories a little bit this way, we might come over one of these big impact structures. And then we talk with the trajectory folks and say, you know, is that easy to do or is that hard to do? And easy or hard usually means the use of fuel. And we want to conserve that fuel because we'd like to have an extended mission afterwards. So it's a trade and a discussion, but really anywhere we go is going to be fascinating at Europa.
One question, though. Europa is tidally locked, right, like the Earth's moon. So it's not spinning, and you're not going to see, you're going to go by the same two faces, or roughly, same two hemispheres every time, right? I wondered about that, yeah.
More or less, as Jennifer showed. You want to take it there?
Yeah, what I would add to that is, you know, there are a lot of constraints on the different kinds of measurements that we want to take. There's certainly features that, you know, hey, if we can scoot over a smidge and get this particular feature that we have some history with, that we know to be interesting already, we certainly can do that. We also have a number of other constraints on the measurements, like lighting conditions. We certainly want to cover things as best we can within the constraints of this, you know, sort of concentrated on the two hemispheres scheme. But we also, you know, have to, there are some investigations that really benefit from having crossovers, and crossovers with particular characteristics, or crossovers like, for example, of the radar tracks, but also having some imagery to go along with that that lets them tie back to models. So there's a tremendous infrastructure to try to communicate between the science team. What are all of the details that help them when they build up the science? And you know, and that's hard to communicate. It's hard to identify and communicate that in a way that we can turn that into, we know to go for this. We know to try to do that. But that's one of the reasons why it's such a great collaboration between the science team and the engineering team.
Are you afraid you're going to miss something?
Well, Again, in the ideal world, we have an extended mission where we can say, okay, we've learned all this stuff, right? We go in asking specific questions and having specific requirements, and then we're going to learn all these new things and say, okay, now in an extended mission, can we go in and go after that monolith that we saw earlier in the mission, or specific areas that show evidence of hot spots or organic materials. So we'll be able to go after those new questions.
That's why we're agile, right? Exactly. Thanks for that one. So here's a really interesting question. So Karen in her slide had a couple of plumes that were illustrated, and we talked about that briefly. So I'm going to ask Bob, given the instrumentation that we have, can we actually fly through a plume, and do we have the sensors on board to be able to do anything with that?
Absolutely. So early in the mission, we'll be searching for plumes and trying to understand, are they real? Are they there? Where are they? Are they sporadic or continuously active? And maybe we'll fortuitously go through a plume, or maybe we'll be able to adjust the orbit slightly in order to go through a plume. And if we do, then our in situ instruments, especially the mass spectrometer and the dust detector, will be able to sample that material in extreme detail to search for organic materials and to understand the detailed chemistry of Europa's interior. Now, if there are plumes, they're not necessarily coming from the ocean. Europa and Enceladus are different. Europa has much higher gravity. They may be coming from lakes within the ice shell, within the more shallow interior of Europa. But absolutely, that'll be a fantastic finding. But that's essentially bonus science, not required by the mission. But I sure hope it happens.
That'll be awesome. We're there for that.
Are there microbes in the plumes? Do the Europanians have jokes about getting too close to a fissure in the ice and getting shot into space?
Out there.
Wah!
So recall, we're a habitability mission. We're trying to understand, is Europa a habitable environment? We're not a life search mission.
No, I kid because I love. But what are you going to say, but?
But if Europa's interior happened to be rich in organic microbes pouring out of it, we would be able to tell from the mass spectra, possibly, that we're sensing life. That's a long shot, but it's not impossible.
It's just so romantic, though. Amazing.
So we are drawing down on time. I'm going to try to get to one last question, and I'll pose this one to Jennifer. So, we have this tour where we're flying in orbit around Jupiter. If we have the opportunity to do so, and another moon, because there's plenty of them out there in Jupiter, in the Jupiter system, if we fly by some of the other moons, are we going to be able to image them at all?
So right now in our plans, we do not have science associated with the other moons of Jupiter. I'm waiting to see what look Bob gives me. Now, it's certainly true that there can be benefits in terms of trying out systems. I mean, in addition to potentially taking measurements, when we're close, doing flybys or things like that. There could be benefits to testing out equipment or getting a feel for the system earlier on, but right now that is not part of the baseline plan.
All right.
Don't have any requirements for headquarters to do anything but Europa. In fact, we've been told to do just Europa. Theoretically, we could do all of that, but that's not what we're planning to do today.
We have plenty of awesome science that we plan on getting back from Europa itself, and that's what makes this mission. So it makes me really look forward to seeing what happens in the years to come as this mission evolves and we get to Europa and get all that science back. It's really exciting to be part of this. I think that's all the time we have, but Bill, if you don't mind, can you click forward once? Oh, you got the clicker. Oh, we got a clicker here. I don't need you, Bill, sorry. So again, I wanted to thank you guys all for joining us this afternoon. I hope you guys had a fun time hearing about all this, but it's a... You messing with me? He's messing with me here, There's a cat. He let it out of the bag. All right, but just to give you an idea of where we were and where we're going to be going. This picture up here is from the Galileo spacecraft taken in the late 90s. A Currently, this is the highest resolution picture we have of Europa. And you can see that scale, that white line is about half a kilometer. The resolution is 6 meters per pixel. Now, as Bill mentioned, why would anybody want to send a spacecraft into deep space without putting a camera on board? Well, the ICE camera is going to take pictures at this level of resolution, a little bit better than an order of magnitude better. What you're seeing here is a picture of Antarctica taken by a different spacecraft, but I wanted to illustrate to you that after we're all collectively done with this journey, how much more are we going to learn about this moon? On the left is where we were, on the right is where we're going to be. But it's even better than that, because the resolution is going to be so good in certain places where we have our closest flybys, is that I want you to focus in on that one section there. That's how good the images are going to be. That's how good the data is going to be from this mission. And I invite you guys all to stay with us, follow us throughout the life cycle of this mission as we work towards launching in a few years, and then the journey to Europa and all the excitement that we're going to bring back. Thank you very much, and I hope you guys have a fantastic Congress for the rest.